learned that we could look at what goes in versus what comes out, and we can calculate fractional conversion. And if it's 100%, that's great. All our reactants turn into products. If it's 10% and only 10% of our reactants turn into products, we have a lot of stuff coming out that we paid for, that we might want. So what's the solution? The solution is we want to put a separator, get our product out, and then take the unreacted raw materials and bring it back and bring it into a mixer. So we'll have a recycle stream. We will have a fresh feed stream. Fresh feed. And then, so our fresh feed, we bring in fresh reactants, we'll mix it with the recycle, and then we'll have a mixed set of feeds to the reactor, and then outputs from the reactor, and then the separator. Okay. And all of this hinges on FC. This FC, but there's actually two FCs once we draw it this way. This FC works if our system is the reactor, and we're looking at what goes in and out of the reactor. I could also look at what goes in and out of the whole system. If I took my system as the entire process, so from here all the way to here, then I have another fractional conversion. That is going to be my overall fractional conversion, and then for the one that's just one time through the reactor, we're going to call this the single pass fractional conversion. Okay, so the first example is a low conversion recycle, and we're going to do ammonia synthesis. So we've been talking about ammonia providing all of the nitrogen, or a lot of nitrogen for our, to create food, fertilizer, and our own food. And it turns out that the ammonia reaction, the Haber process, is not all that efficient. It's equilibrium limited, so you cannot get 100% in a single pass through. You're going to be somewhere more along 10 to 30%, something like that. So let's say, so this will be our setup. We'll have a mixer and a reactor and a separator. And let's say we're given a basis of 1,000 kilogram moles per hour of NH3. I'll make 1,000 kilogram moles per hour of ammonia. And let's make a couple of assumptions. Let's say we have a stoichiometric feed ratio. Okay, so what's that mean? We talked about excess and limiting reactants. We're not going to have any of those. We're going to mix. What's the feed ratio going to need to be for nitrogen and ammonia? For the nitrogen and hydrogen? 3 to 1, right? Because we're talking about N2 plus 3 H2. We're going to go to 2 NH3. So, okay, so stoichiometric feed ratio. The other thing to make this as simple as possible is I want to make the separator really easy. So let's assume we have a perfect separation. So let's assume all the ammonia comes out as the product, and all of the unreacted nitrogen and hydrogen we can separate out and recycle. All right, so let's find, what I want you to find is the molar flow rate of N2 in stream 1. So how much nitrogen actually goes into the reactor. And I want you to find that as a function of the fractional conversion. So let's say the fractional conversion is 10%. How much nitrogen do I have to put in the reactor? What's the flow rate going into the reactor? That's going to be important because I need to know this flow rate so I can size this reactor. So if I need to know how big a reactor to buy, how to set up the process, how much is going to flow through and recycle based on different fractional conversions. All right, how many variables? How many streams? 10? Molly says 10. You want to disagree with Molly? Disagree with Molly. How many agree with 10? You want to list them out for me, Molly? What do you have?
The fresh feed has
Nitrogen, hydrogen, the fresh feed.
and the one also has nitrogen.
Okay, stream 2.
Ammonia and nitrogen.
Nitrogen, hydrogen, ammonia. Product.
Okay.
Ammonia, recycle stream. Nitrogen and hydrogen. So is that everybody count 10?
Yep.
How many reactions? 1, so it looks like 11 variables to me. How many specified flows? 1 or 2? 1. Which flow? Okay, this to me looks like n dot of ammonia in the product equals 1,000 kilogram moles per hour. That's this guy here. Okay, one stream question, Daniel.
Yeah, for variables, like, shouldn't you not necessarily worry about what's inside if you're gonna like look at, since you know the overall 1,000 kilogram moles, meaning like with the recycled product, there's 1,000 kilogram moles of ammonia coming out. So what if you just have fresh ammonia, fresh hydrogen in, as 2 variables, and then 2 variables for ammonia and hydrogen recycled going back in, and then 1 for the reaction itself. So 6 variables.
You want to eliminate 4 of my streams?
Yeah, the like NH before that goes into the reaction. Shouldn't that just be all the variables added?
It is. How do you know that?
Isn't that redundant?
This nitrogen is this nitrogen plus that nitrogen. How do you know that?
It's a mixer, so there's nothing.
So the equation is that tells you that is
Material
material balance.
balance.
So we'll count that in our material balance. So yeah, you're right. Okay, so if Dan, if you want to put the mixer in the reactor, put both of these arrows in, you could do that. This might be a case. Today what I'm doing on the board, separating these out, will show some extra steps in the math, but I think it'll still work out. How many, okay, so 1 specified flow, how many stream specifications? 1, which is? He's documented feed ratio, so n dot of nitrogen in the fresh feed equals something related to the hydrogen in the fresh feed flow rate. Where's the 3 go? Left or right? I need more hydrogen, so I better multiply the nitrogen by 3 to get my hydrogens. Okay, so there's an equation. System specifications. 2? I don't hear anything. Okay. Material balances. How many material balances? 3? There's 3 components. Okay, we did this with multiple units before, right? How many do we get? What do we do with multiple units? Depends on our system, right? So if you pick the whole thing, you've only got 3 balances over the whole thing, but let's go unit by unit. How many material balances for the mixer? 2 balances for the reactor. For the separator. 3. Okay, so we've got 8. Looks like 10 equations, 11 variables, yes? Fractional conversion. What about the fractional conversion? That would be a system specification, exactly. So the one here is FC equals, is a given? No, but we're going to set it. We're going to do this as we're going to assume it's known, and we're going to let FC vary, and we're going to get some equations.
What about these separated? Does that count as a system specification? Because it like splits again.
Yeah, that's a great question. We have perfect separation. What does that information tell us? All the ammonia comes out here. All the nitrogen, hydrogen comes out here. So how does that go into our DOF? Nikhil?
Well, I guess since you don't have stream variables coming out already, you don't need to include it. But maybe if you actually wrote out nitrogen and hydrogen there, like, and counted those as variables, then you could say you have a system.
So if I have those variables there, then I have 3 more variables, and then yes, that would well, The perfect separation tells me this one's 0, that one's 0, that one's 0. There's three more equations, 3 more unknowns. So if you on an exam gave me 3 more stream variables and 3 more specs, yeah, I'd only take out half the point because you got the right content. You're just making it a little more complicated for yourself. The easier thing to do is just not even put those variables up there at all. No variables, we don't need equations. If I told you it was the separation, if I told you 50% of the ammonia came out of the product stream, that's one system spec of the separator. We'll go over all this after spring break. We'll do the separations chapter. Manish.
So is that kind of considered in the material balances, the fact that it's 100% separation? Since you only have 8.
No, it's just in naming the variables. I'm not even putting a variable there to solve for. So with FC, if I specify FC, then I have 11. If I make up an FC, if I say let's let FC equals 50%, then this is solvable. Or 10% or whatever. Or I can solve the whole thing as a function of FC. Okay, so where should we start? What should be our strategy? We have 2 strategies for multiple process units. What were they? We can go unit by unit, and we can write material balances. Or we can wrap the whole thing, call the whole thing a system, we can do the whole thing. Which should we do? What's your intuition say? Which way is best? How many want to go the whole thing? How many want to go unit by unit? What about split? Okay. Let's start with, let's go unit by unit. Let's do nitrogen in the mixer, nitrogen in the reactor, nitrogen in the separator.
And dot plus dot and the cycle equals and dot and
Great. Everybody around Youngsu agrees? Is that what your cluster has? Okay, and Waisha, what do you have for the reactor?
N dot N1 equals N dot N2 plus the V, but I don't know what exactly. Mu, there we go, sorry. N2 C dot. Yeah.
Great. Everybody agree over here? Okay, and Noah, what do you got for the separator?
N dot N2 equals N dot NR.
You got these. Great. So what comes out of the reactor just gets recycled. Great. So where are we? Can we solve these yet? We know the fractional conversion, right? Can we write this equation in terms of the fractional conversion? I assume that's given. So what goes in equals what comes out plus what gets reacted. It'll be the same as what goes in equals what goes out plus fractional conversion times what goes in. That's the other way we could write that with the fractional conversion. These two are equal. And the recycle is here is N2. Let's see, let's plug in the recycle. Let's plug that in there. So we have N dot N1 equals N dot fresh feed plus N dot N2. And then here's the equation with N1 and N2. I'm just trying to eliminate stuff. I can rearrange this and say N2 and N2 equals 1 minus FC times N dot N1. Just collecting N1 and N2 together. So now I've got N2, I can plug that in there. Now I can get N dot N1 equals N dot and then the fresh feed plus 1 minus FC N dot N1.
Then when you just have N dot.
N1 goes away, right? That's a minus, so N dot N fresh feed equals FC N dot N1. Let's see, so the fresh feed is equal to the fractional conversion times what goes into the reactor. Does that make sense? Can we think of why that makes sense physically? Okay, so whatever goes through and doesn't get reacted comes back around. What does get reacted, I need to replenish with the fresh feed because everything's at steady state. So this makes sense. Okay, so that's good. I did my math right. Fractional conversion tells me how much I got to replenish each time. Okay, let's do ammonia. And how should we do our balance for ammonia? Let's do the whole system. Let's think of the whole system. Fresh feed and product coming out. Let's just lump the whole thing in one box. And yeah, so this is our whole process. Cool. So the amount of ammonia in the product is the amount of ammonia generated. The amount of ammonia generated is the extent of reaction times the stoichiometric coefficient. Cool. And we have numbers for this, right? NAP is 1,000 kilogram moles per hour. What's nu A? That's 2. Cool, so we have our extent of reactions. I dot is 500 kilogram moles per hour. There's 500 kilogram moles per hour of the reaction, our overall reaction. Cool, we'll add N dot of N, nitrogen balance, somebody over here. N in the fresh feed, N equals generated?
Consumed.
Consumed, is this consumed?
Yeah, it's consumed.
In plus generated consumed. This is our, yeah, that's our nitrogen, right? Our dot of nitrogen. So yeah, so we got a sign there, but we're pretty close. Okay, great. Nu dot of nitrogen is 1. Psi dot is 500. So N dot. Oops, sorry, this is minus 1. N dot minus 500 equals 0, so we get N dot nitrogen in the fresh feed equals 500 kg mole per hour. Great, that makes sense. Everything that goes in has to, at any given moment, it's getting mixed with all kinds of stuff. There's the extended reaction is 500 kilogram moles per hour, that much comes out, that much has to get consumed at any given second, that much reaction has to happen, so I've got to replace that much fresh feed. I don't know if I said that clearly. So remember when we did multiple process units, we said we could do unit by unit, you could do overall. In this case, you need to do both. The overall is going to give us psi dot, and then the unit by unit is going to let us solve. Actually, we're asked for flow rate of 1, of stream 1, so you can't even get that unless you do unit by unit. You've got to do both. So we have this equation, N dot fresh feed is FC times N dot N1. We solve for N dot fresh feed. So now I can get N dot N1. N dot N1 equals N dot N fresh feed divided by FC. So N dot of fresh feed doesn't care about the fractional conversion, it's constant. Blow your mind, okay. So but that's 500 kilogram moles per hour divided by FC. The flow rate here is 500 over FC. Let's see if we can understand that. Does that make sense physically? Fractional conversion. N dot N1. Fractional conversion goes from 0 to 1. So fractional conversion is 1. Then the N dot of fresh feed is 500 kg moles per hour. As fractional conversion goes to 0, what's N dot 1?
It represents infinity.
It's infinite. Okay. And in between, this looks like 1 over x, right? So 1 over x is yeah, something like that. Does that make physical sense? So fractional conversion, how much reacts in a single pass? So if fractional conversion is 1, everything reacts in a single pass. We only get ammonia out. There's nothing to separate. The product comes out, and the flow rate here is 500. What we put in is 500. As the fractional conversion goes down, if it were 0, we'd have no ammonia. We'd have all NH. It would all come back and get recycled. Now you can do your time thing. It keeps getting recycled and recycled, and what happens to the amount in the reactor? Goes to infinite. So that's steady. This is the steady state solution. There is no steady state solution. You'd have to have an infinitely large reactor, not this reactor. But let's say 50%. Let's say we had 50% conversion. Now the fresh feed rate is twice that. That'd be 1,000. So that makes sense. Maybe if we put 1,000 in, we'll react 500. We'll get 500 out the product. We'll recycle 500 back. 500 plus the 500 in the fresh feed gives me 1,000. It all works out. Yeah. If it's 10%, we'll need. If it's 10%, we'd have 5,000 here. We'd react 500. 500 would come out. 4,500 would come back. We'd get 5,000 here. Okay, so the lower the conversion, the more we have to recycle around. And what happens to the reactor? The flow rate, it's bigger and bigger. Okay, so in this range, we're going to have, we started with single pass FC, and we have overall FC. What's the overall FC? 100%. Everything, the overall is 100%. But as the single pass goes down, we need a large reactor volume, and flow rate. And there's two downsides to this. What's bad about a large reactor and flow rate? It's going to cost me more. What else? The second one's a little more subtle. Why might you not want to have a large reactor? Safety. Let's say we do have a blowout. It'd be much better to blow out a small reactor than a large reactor, right? So you always want to keep the lines of chemicals low in your plant. All right, so there's recycle. So when do we use recycle? It's pretty useful, right? We took our 10%. We got rid of all this waste. When to use recycle? Low fractional conversion, that's where we started. If we're not converting enough, we want to recycle. How low is too low? Well, what are we trading off for maybe to recycle? What do we have to do instead? Instead of just letting all the fresh feed go out with the product and wasting it, so we have the price of the fresh feed versus the price of cleaning it out of there, right? So what we're looking for is the separation must be feasible. First of all, you have to be able to separate the product and the reaction, and then that means cheaper than the cost of raw materials. And cost there might just be cost off the shelf, but it might also be EPA and environmental considerations. Overall, is it better to separate or to get new stuff? It might depend on cost. Sometimes you might just want to have that. Okay, so a lot of times this comes out in commodities. Commodities are high volume. If you're going to make plastic, you're going to use a lot of stuff. It's going to be worth your while to recycle. Even if the fractional conversion is 90%, you might want to get that 10% back and put it back into the process. Let's say we still want to make 1,000 kilograms per moles of ammonia. But let's say the nitrogen is not pure. Let's say N2 feed has 2% argon. Why would I get argon in the nitrogen feed? The atmosphere is like 0.75% argon. So if we're just separating nitrogen and oxygen, we're going to end up with argon in our nitrogen. What's argon going to do in this process? Is it more or less volatile than, let's see, when we do the separator, where's it going to end up? With the ammonia liquid or with the nitrogen hydrogen gas? Gas. Okay. So we're going to have our argon. Let's see. So we're going to have argon here, argon on the feed, argon in stream 1, argon in stream 2, argon in the recycle. What's going to happen? Get the argon out of the system. The argon is going to build up and build up and build up. So first of all, this happens. You build a plant. You might not even know. It might not be 2%. It might be 0.02%. When you start doing this, you're going to get some buildup. So, and it might be something you didn't know was in there. So this happens. What do you think we should do? Got an intuition? Maybe?
I have an idea that it's possible, so
Throw it out there.
trying to get something in there with it to react with the argon.
I like it. Reactive. Reacting the argon away. Why won't is that going to work? That's a great solution, actually. Reaction is a really good alternative to separation. If we can react something, we just get rid of it. We don't have it. What's the problem with reacting argon? It's inert. So good. I like the idea though.
Can you not just put another separator with the recycle?
Put another separator. Get it out of there. Where should I put the separator? After the first separator. How do I separate argon from nitrogen and hydrogen? Splitter. We're going to use a splitter here. How's a splitter different than a separator? Same composition. So if I've got nitrogen and hydrogen here, I'm also going to have nitrogen and hydrogen there. Excellent. Okay, that's the thought experiment. Our nitrogen balance used to be really easy. 500 went in, 500 got reacted. Now we've got, okay, so now N1 equals opposite mu N psi dot plus N in the purge stream. So this is called a purge. So this whole thing now is called recycle and purge. And yeah, okay, so now this gets, now things are going to depend a little more tricky, yeah. Splitter. We're going to talk about splitters. The specification on a splitter is called a fractional split. And we're going to have some fraction of stuff split off. So we're going to say F fractional split of stream B is N dot of argon in stream B divided by N dot of argon in stream 1, 2, 3. Let's call this stream 3 there, and 3 in stream 3. I'm going to have to set this value. This is another specification. It's a knob I get to turn. How much do I split off? I can split off 10%, 1%, half. The more I split off, what's the disadvantage? I'm going to waste my hydrogen and nitrogen. The less I split off, the more argon's going to build up. So we'll have a cost-benefit trade-off there. Okay, so that makes sense. We're going to have to set this now. So now what I ask, the question originally was find N dot N1 as a function of fractional conversion. We're also going to need it as a function of fractional split because it's going to change things. I'm also going to want to know how much argon is in stream 1 based on fractional conversion and fractional split. Splitters don't care what it is, it just puts things out different sides. So this fractional split is also the same as N dot N in stream B and N dot 3. If I take half of the argon out, I'm going to take half of the nitrogen out too. I'm going to take half of the hydrogen out. Here's two equations. These are two splitter equations. If you go back to Murphy's degrees of freedom, she says if you have a splitter, you get n components minus 1 times number of streams minus 1 equations. Those are your two equations you get here. Number of components, 3 components minus 1 is 2 equations. And your degrees of freedom, this will help it work out. I'm going to write a couple formulas and some graphs here. M dot N in the fresh feed is now going to care about conversion. And fractional split and fractional conversion. Fractional conversion over fractional conversion. The amount of nitrogen you have to put in the fresh feed is not going to depend pretty complexly. You can derive this. I've got 4 pages, so I'm not going to do it on the board. I can do it if you want. My derivation, email me. Murphy also says I'm not going to show you all the steps. So if you want me to post it, email me. Let's see. N dot argon in stream 1 depends on how much argon comes in, times xi dot times Fs, 1 minus Fc plus Fc over Fs plus Fc. You know what, you can, I think these formulas are, let me show you a graph and then we'll be done. N dot argon is stream 1 versus fractional split. If fractional split is 1 versus, if we split off 100%, what does that mean? 100% goes here. There's no recycle. That's the no recycle limit, which you already know how to solve. And then the argon that goes out is the argon that comes in. As you then cut it down to fractional split is 0, that's the, everything gets recycled here, which you told me it's going to blow up. So the argon that flows through goes to infinity. If I plot the overall Fc, that does something similar. It goes from one value to another. So you get more overall, sorry, the more you turn down the split, the more conversion you get. In the winter.